Hello everyone. Today we will walk you through our project on predicting airline passenger certification, combining data modeling with actionable business strategies. And I will be introducing the background of our project, our main objectives, and the data sets we use. We select the airline certification dataset for three reasons. The airline industry is a classic high-contact services field, where customer satisfaction heavily influences loyalty and revenue. And the label is binary, satisfied versus dissatisfied, and the features are mostly structured and numeric, making it highly suitable for ML modeling. We use a structured dataset from Kaggle that contains clearly labeled satisfaction scores, making it suitable for both machine learning and business insights. And the project has three goals: to build a prediction model, identify key influencing features, and produce business recommendation based on results. The data size come from Kaggle and includes 130,094 records across 24 columns. It contains demographic views, example gender, class, loyalty status, service rating, example boarding, Wi-Fi, feed cleanness, and dwell times. The targets for variables is satisfaction, categorized as satisfied or neutral or dissatisfied. And our project methodologies includes the following steps. 1. Data pre-processing. Handle missing values, outliers, and apply feature scaling. 2. Model training. Try multiply algorithm, including logistic regression, decision tree, and MLP. And 3. Model tuning and evaluation. Apply hyperparameter tuning, cross-validation, and visualize performance with confusion matrices and ORC curves. 4. Business interpretation. Turn results into strategies and operational recommendation for the airline. Okay, we'll move to next one.
So let's jump into the data exploratory and pre-processing part and also the ADA summary. Although our dataset was relatively clean, it still requires some format adjustment. For example, showing the table on the left, for our travel clause, we use one-hot encoding. So we choose business clause as our baseline. These transformations help us to prepare a fully numeric, consistent dataset and ready for the later training predictive models. And once our pre-processing was done, we explored the data to understand it better. So first, we checked for our missing values, and there's no missing values. Next, we examined clause and categorical imbalance due to the 3 bar charts at the corner. So the target variable, our passenger satisfaction, is fairly balanced, about 55 satisfied point visas to 45, and so as the gender. And however, we noticed that a strong imbalance in the customer tab. Around 81% of passengers are loyal customers. So this means that our model may be more biased towards that group. So we keep this in mind when interpreting results later. So let's focus on our numeric features related to each other and to our target variable. So features like the online boarding, seat comfort, and in-flight entertainment, which is tagged by the heart in our heat map, are strongly correlated with each other. So for the tree-based models, can handle this overlap naturally, but for the linear models like the logistic regression, we will monitor using tools like VF. And then we focus on the overall background showing the heat map. We saw a very strong correlation between the departure delay and the arrival delay. So to avoid redundancy, we just keep only one arrival delay. And then if we focus on the target variable satisfaction from the arrow in the left, there are 3 features are likely to play an important role in the predicted satisfaction. And we will revisit them later. Finally, so there's no other variable pair had a correlation greater than 0.8. So overall, the dataset doesn't suffer from the excessive. And then we jump to the second part. We also look at the feature skewness. First, we observe the highly right-skewed departure delay, arrival delay. So for those, we consider applying log transformations or use on robust models. And we also have some mild score and also the zero score. It is about the service rating variables like some seat comfort and Wi-Fi quality. So overall, our skewness analysis gives us confidence in using 3 models without heavy pre-processing.
I will introduce modeling strategy and baseline construction. To evaluate the predictive performance of different classification algorithms on airline passenger satisfaction, we built and compared 6 models. The first one is logic regression. It's a transparent linear baseline for interpretability. The second one is decision tree. It can capture nonlinear relationships, easy to visualize. And the third module is MLP natural network. It can handle complex features, interactions on the nonlinear patterns. Then is the rainforest. It's a robust ensemble method based on bagging. Then is XGBoost. It's a powerful boosting algorithm optimized for speed and accuracy. Then the last module is LightGBM. It's an advanced boosting method offering the best trade-off between performance and efficiency. As you can see in the picture, this tree shows how online boarding, Wi-Fi, and entertainment are key factors. Poor scores in this lead to dissatisfaction. Orange notice predicts unhappy passengers. Blue means satisfied. It's simple, clear, and helps airlines know where to focus to improve satisfaction. Then I will introduce hyperparameter tuning via search survey and feature selection. To improve module generalization, we applied the grid search survey to tune key hyperparameters for the following modules: logistic regression, decision tree, and MLP. Grid search allows us to find optimal settings while avoiding overfitting. We additionally explored feature selection using select k-based, which helps retain only the most statistically relevant features to improve module performance and reduce overfitting. As you can see in the picture, we used 5-fold cross-validation and selected FE score as the main evaluation metric. Advanced modules like Random Forest, HB-Boost, and LightGBM were turned via their internal optimizers and default configurations. After training and tuning, we compared the 6 models using 3 evaluation metrics on the test sets. Here are some insights. GBM outperforms all other and is recommended for deployment. Logistic regression, while slightly less accuracy, is highly interpretable and suitable for business dashboards. Ensemble models effectively capture nonlinear patterns and handle feature interactions. There's some deployment plan. Use GBM for backend prediction pipelines, with logistic regression for transparent reporting in business dashboard. As you can see, the chart shows module performance across 3 metrics. GBM leads in all areas, followed by XGBoost and Random Forest. Logistic regression performs lower but offers high interpretability. This feature confirms that ensemble models deliver the best predictive power.
Thanks, Jiatong. I will compare 3 classifier logistic regression, decision tree, and an AAM before and after tuning. The default logistic hits 76% accuracy. After regularization, feature selection, and grid search, it jumps to 87.2% accuracy and 0.85 F1, a plus 10 pp gain with no extra overfit. Here are the 10 logistic odds ratios. Online boarding double satisfaction odds, OR equal around 2.24. Personal travel and disloyal customer type each cut odds by over 50%. Service quality ratings rise odds modestly, while delays hurt them. Baseline logistic has precision 0.72, recall 0.76. After tuning, when C is 0.01 plus selects the best, the precision goes to 0.87 and recall to 0.83, a clear reduction in false alarms and better true positive capture. For the decision tree, tuning entropy split max death is 20, while the sample per leaf is less than 5, yields a 2.7 point precision gain with recall virtually unchanged. We flag far fewer false positives without missing dissatisfied flyers. Accuracy rises by 1 point, confirming that this linear tree strikes the sweet spot between the complexity and the generalization. This result is a clear, reliable rule set for targeting service fixes. And ANN soars from 85% to 96% accuracy, and F1 from 0.83 to 0.95. Precision and recall both jumps over 10 pp, and train and test gap stays under 0.3 pp. Stronger generalization from 100 neuron layer. This summary compares all 7 configurations on the same axis. Logistic regression tend to 87% test accuracy, minimal gap, and decision tree default overfits 100% train, but 10 reaches 95.3% test accuracy with half the gap. The ANN tend to 96% accuracy and F1 0.954 near zero gap. The random forest lists at 96.3% accuracy, and F1 is 0.957 with a moderate gap. The recommendation is for peak performance, use the 10 random forest. For interpretability, we prefer to choose the 10 decision tree, but for best generalization, optimize for the 10 ANN. Finally, the ROC curves and the accuracy comparison show models closer to the top left corner are better balanced. Among our 10 models, Light GBM achieves the stronger ROC performance. I will now hand over to my colleague, who will translate these findings into actionable steps for enhancing customer satisfaction. Thank you.
Here's the line. Coming to the end, I will share some business insight we have gained during this process. First, application of the model in practice is listed. Talking about the role model, the first keyword is decision-making door. Our model more likely to deal with a large volume of data. The second function is a model could be a real-time predictor, fastly responds to the customer satisfaction based on survey results. Moreover, this model could effectively classify the passenger according to their profile, establishing customer segmentation model. On the right, you may see some application of our models in practice. It's supposed to generate the feedback based on information collected during or after the flight. It could also be deployed as monitor of customer retention, arrange regular revisit, and special follow-up for customer according to feedback. Besides, the model could evaluate matters related to user experience, providing instructions on allocating resources. In this case, we'll give several recommendations based on our research outcome. The primary task is to modify training content for flight attendants according to the correlation with satisfaction. Secondly is to enforce a reactive strategy, actively contact passengers who tend to be dissatisfied with the flight, with discounts, preventing the loss of customer. Another inspiring result is the impact of the factors out of the plane on satisfaction are stronger than we expected, including gate location and ease of online booking, emphasizing the significance of ground service quality. However, our research inevitably has some flaws. The first limitation we found is the class imbalance in training dataset. At the data pre-processing stage, we discovered this issue as the more survey shows that more passengers are neutral or dissatisfied with the flight. This is the model more likely to predict negative outcome. So random forest applied in our study mitigate the impact and increase the minority samples. Another concern is data sensitivity. So talking about survey, there is an unignorable subjectivity and it's possible to verify. So our suggestion is to optimize and simplify the survey question design, and we exclude some weak-correlated factors in our study. In this flowchart, you may better recognize our workflow. Starting with data pre-processing, we clean and transform the raw data to make it suitable for analysis. Move on to model building. The 3 models applied in this research: random forest, gradient boosting, and combined models. Afterwards, we conduct evaluation of models and go through hyperparameter optimization. With conversion performance before and after hypertuning, we realize its important and enhancement towards models. Based on that, we obtain 4 business insights and raise ideas of application of models in reality. Of course, no model is perfect, so we also made some limitations, but we also figure out the corresponding solution to it.